when I was out west one time, I went through a something like a Taco Bell, but it wasn't a Taco Bell, and it was through the drive-through, and they had something that was called a whole lot of box. And I'm getting ready to tell you that this biodiesel lab is a whole lot of box, because there's tons of different things that you're going to have to do on the inside in order to get this lab completed. So not only are you going to have to wait for days and days and days and days and days, but there's going to be multiple tests that happen after the fact for you to test the quality and the purity of the biodiesel that you have made in our laboratory setting. So what you're seeing on the screen right now is a current version of our biodiesel lab, and I want to talk a little bit about what's going to happen hands-on in our lab environment, because you've already went through lecture video after lecture video after lecture video after lecture video of lecture stuff about biofuel and biodiesel and the whole importance of what this can bring to the table. So here in the background, you're going to see a small blurb about the types of reactions that are happening in this lab experiment. So first off, what I want to talk about here is this idea of what we call trans-esterification. Trans-esterification is a organic type of reaction that goes on, in our case, in a huge big reaction flask. And what happens, trans means to convert, right? So we are converting esters because it says esterification. So what's happening typically is that we're starting with one type of ester and we are making a new one. So what you're seeing on the screen down here at the bottom in the reaction, here is our ester functional group. It's right here. And this is what we're starting with. That is an ester group, and this is an ester group, and that is an ester group. So these three esters can all be the same. The three esters can all be different. It does not matter. So with that said, where does this come from? Like, what is that supposed to represent? This is supposed to represent our oil. Now, it says vegetable oil here in the example problem, but I want you to keep in mind that any oil is actually going to work. Vegetable oil, canola oil, peanut oil, even something like lard. We just have to heat it up and get it warm, and we're going to have to do that anyway. So with that said, an oil is an oil, a fat is a fat. It does not matter. So these esters are going to be very, very important for us because that's what we're playing off of. And good news, any oil is actually going to work. So these are the starting esters that we are kind of adding to our reaction flask in the beginning of the lab procedure. And then we're going to add some alcohol. And this alcohol in our example is going to be methanol for most of the time that we do this lab. And that methanol is going to react with the vegetable oil. And then we're going to go chop, 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 chop. And then what happens is that these esters will actually free, and they go, and yay, they're on their own. So that's why you will often see a coefficient of 3 out here in the very beginning, because they're letting you know that you have just chopped all of those ester groups in the beginning. Those ester groups are now freed, and what's happening here is that the types of alcohol that you use, it could be methanol, it could be ethanol, it could be propanol, it doesn't matter, it's an alcohol. This reaction is going to work, but in our situation, we're going to be using methanol. So when methanol reacts with that ester, what you're going to see is that the R group, so CH3OH is methanol. So this R group, which is a methyl group, that's what that R stands for. Again, it's a template. It means any alcohol is going to work, but in our situation, methanol is CH3. That CH3 group is going to attack and chop, 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 chop that side of the ester off. So that's why we have what we call an R prime and an R double prime. The R prime here is going to be our CH3 group from the methanol piece, and the R double prime is whatever is on the outside or the other side of this ester group. And this is what we call our biodiesel. It is a group of really not quite hydrocarbons, but carbon-based compounds, so organic types of compounds, that all have ester groups on them, and these can be used to give us energy, and these can be used in order to move some wheels on a vehicle, or do other purposes, whatever you decide to do with it. Next up, the other product of this, we have this chop, 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 chop that happens out here on the ester side. So what we're left with now is a C and a C and a C, 3-carbon chain, and then these still have the hydrogens on them just like before. I mean, there is no difference here with those, so that's okay. But then we have this open side that is just now went chop, 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 that something has to go on, right? So what things go on to that carbon, so that way carbon can have 4 bonds in total, because that's the whole name of the game with the octet rule. 4 carbons or 8 electrons. I learned that in general chemistry. Look at me. Whee! All right, well, what goes on there is this OH group from the alcohol piece. So an OH is going to go here, and an OH is going to go there, and an OH is going to go there. So when that forms, that is a new product, and that new product is represented over here, 3-carbon chain, all with OH groups, and that is called glycerin or glycerol. It goes by both names, and it means the same thing. All right, so overall, this is the reaction that is going to happen when we start mixing these things together in the lab. A very easy reaction, I might add, to take place. However, it does take quite a bit of time. So it needs a little bit of help. It needs a little bit of patience. But as far as getting the reaction to go forward, there's nothing that I need to do as a user in order to make that happen. I just need to give them a nice little jacuzzi tub for them all to sit in and hang out, so that way they'll get to know each other along the course of time while they're spending that together. All right. So the reagents here, they're going to list the triglycerides, which are the vegetable oils or your canola oils or any type of oils, actually. Tri means 3, so 1 carbon, 2 carbon, 3 carbon, go figure. And then we also have alcohol as the reagent as well. And methanol is going to be the alcohol of choice. It is the simplest, it is the easiest, it's one of the cheapest, and it's something that we always have on hand. So why not? It's going to do a great job in order to make this reaction go forward. So the catalyst, a catalyst is something that speeds up the reaction. So we need something here so that way I don't have to wait weeks and weeks for the reaction to take place, just maybe 1 week instead of weeks and weeks. So that's going to speed up the reaction. It's going to kind of give this reaction the actual jacuzzi tub for them to all get ooh. And then the catalyst of the reaction is going to be our KOH, and that KOH is potassium hydroxide. So this is a base. And I'm also going to include a triangle here for heat. So we do like to warm these up. That is something that we do on our end. You might not see that elsewhere, but we like to do it. So we like to warm up our jacuzzi tub to actually make it a jacuzzi tub. And then that heat along with the base is going to both serve as a catalyst to make this reaction go forward a little bit faster. Finally, the products here are the biodiesel, and this biodiesel is really just this grouping of these ester pieces that have been formed, that have been chopped off of the oils that we have incorporated here. And then glycerin is also going to be one of those products that we're going to see as well. As far as the biodiesel goes, we call this FAME. This is something that we probably talked about in the lecture videos, and that FAME stands for something. And that FAME is going to stand for fatty acid methyl esters. So the ester group, again, is C double bond OO. So that is our ester group, the E for FAME. The methyl group is often regarded for a 1 carbon. So CH3 group, that is a methyl group. It's a 1 carbon containing compound. So that is the M for FAME. That's methyl is coming from our methanol. Ta-da! that we are using in the reaction here. And then on the other side, it can just be whatever kind of random thing it wants to be. So this is what we call a fatty acid, and it is slightly acidic, or it can be slightly acidic. And at the same time, we have this ester group with a methyl on the end. So that overall is the reaction that's getting ready to happen in this lab experiment. All right. As with the lecture, what you probably saw in the lecture videos, just a schematic of the different things that go on in the production of biodiesel, because that's really what we're doing right now. And we normally put everything into a reactor, and this serves as an area for these two things to kind of do what they need to do, make what they need to make, and then over a course of time, things begin to separate. That then gets transferred into a separator, and that separator will drain off the glycerin, the water, the alcohol, all the stuff that we don't need, and we can circle this back around, and we can reuse that and recycle that if we want to. And then the separator will also pull off the biodiesel and send it into what we call a wash column. The wash column will then give us an area that all of our water can trickle through. The cleanup process of the biodiesel can happen in the wash column, and then that way our biodiesel is somewhat trapped and it's not going to go anywhere, but we're also cleaning that at the same time. So once more, water goes in, the water gets drained off, the water can be recycled and reused maybe, and then sooner or later after the washing takes place, we can take that biodiesel, dry it, heat it up, get rid of the water, do what we need to do with it, and then we have hopefully B100, which is our biodiesel product. So in our lab activity, we're going to kind of represent this in different stages, just on a small scale. So we're going to have a reaction flask, and the reaction flask is going to have our reactor. So this is where our vegetable oil and our methanol and our base and our heat is going to be generated. And this is where our products are going to be made. Then sooner or later, after we give that reaction a little bit of time to do what it needs to do, we are going to put it into a separator, and this is a separatory funnel. So we use a separatory funnel just like we've always used a separatory funnel. There is no difference. And that separatory funnel will create two layers. One layer will be glycerin that we don't need, and the other layer is going to be our biodiesel that we want to keep. We are going to use a wash column. However, this is also just really the same separatory funnel that we used before. So we're going to keep our biodiesel in that separatory funnel. We're going to trickle water through that sample, and that water is going to help wash the biodiesel and get rid of all the impurities. And then hopefully we can take that biodiesel, eventually drain it, and then we're going to put this not in a dryer, not in an oven, but on something as simple as a hot plate. So we're going to drive off the water using a hot plate, and that way I can get hopefully close to B100 as a product. So if I take a look at the procedure, there's going to be a little bit of calculation here that you're going to have to do. It says the recipe for making biodiesel from vegetable oil or canola using base as a catalyst is simple. So the reason that I say that is because we've got one or the other. I don't really know if we've got canola or vegetable. We'll have one or the other. This is going to work out no matter which one we have. So we'll put it out in front. We'll let you know which one it is, but don't treat this any different. So whatever oil you get, you use the same ratio and the same type of recipe. So the recipe for making biodiesel from virgin canola or vegetable oil using base as a catalyst is simple. For every 1 liter of oil, you're going to add 200 milliliters of methanol and 8.5 grams of KOH. So this is going to give us an overall reaction that happens here. It gives us an idea of how much product that we're going to end up with. So 1 liter of oil should also give us about 1 liter of biodiesel. I mean, they are almost 1-to-1 in a way as far as volume goes. And then the glycerin that's happening is about the same as methanol. And then there's going to be some other byproducts that happen here as well, like salts and leftover bases that we don't need and we just don't include. We just don't bother with them. It says, however, in this experiment, you will not need 1 liter of oil. That's a little bit wasteful for what we need. Instead, you'll start with 200 mils of vegetable oil. Therefore, you'll have to scale down the amounts. All right, so I want you to think about what's happening here. You have a recipe that is based on 1,000 milliliters, 1 liter of oil, but you really only need 200 milliliters for the reaction to take place and give you enough to do some of the testing with. So we have scaled this down, haven't we? So the recipe was based on 1,000, and then we have went down to 200. So 200 goes into 1,000 by an order of 5 times. So really what needs to happen here for this calculation, if you're going to use 200 mils of veggie oil, you need to take the methanol that they suggest for the 1 liter recipe and divide it by 5. To get the number of mils of methanol that you need here. And the same is going to happen with KOH. Once you see this recipe for 1 liter, you now know you're going to only make 1/5 of that. So that 1 liter divided by 5 gives you 200 mils. That 0.2 liter or 200 mils divided by 5 is going to give you the proper milliliter of methanol. And then just like here, 8.5 grams divided by 5 is going to give you the number of grams of KOH that you need to measure out. All right, so once you calculate this, you need to double check these numbers with an instructor, so that way we can tell you, yeah, you did that simple little math equation the right way. You're measuring out the right amount that you need. So good job. Go on, go forward. All right, so let's talk about the procedure once I have all of my measurements and stuff ready to be taken care of. Okay, procedure. Step number 1, making the crude biodiesel using a graduated cylinder. Whoo, that makes my job easy. We're going to measure 250 mils of canola or vegetable oil. The oil will not be previously used, so no acid titration will be needed. It's out of a new jug. All right, so first off, I want to say, oh, shame on me, because I just told you that we're going to divide everything by 5, right? So the same thing's going to happen here. This is a misprint. It's not 250 mils of canola oil. It's 200 milliliters of canola oil. So that is a mistake. That mistake could be fixed by the time you get a hold of the lab procedure. Maybe not because I'm lazy, but either way, 200 mils or actually even 250 mils would work. You'll just have a little bit of extra leftover oil that will not be converted, that will get cleaned out. Next, place the oil in a triple neck boiling flask. Ooh, that sounds fancy. You could have used a boiling flask already. Here it is. And then triple neck. Triple means 3. 1 and 2 and 3. So there's a reason that we want this. And we're going to talk about some of these reasons here in just a minute. But this is maybe your first time using a triple neck flask. So in goes the oil. And it says submerge the flask in a hot water bath that's heated to 55 degrees. So that entire flask is going to be lowered. Now, just the flask at this moment, that flask is going to get lowered into a 55 degree water bath. And we want the oil to be 55. The water bath can be 55, but if I dunk the oil into the water bath, immediately that is not going to be 55. Use common sense, right? So when you put the oil into the water bath, it's going to take some time for the oil to get to 55. So that's why we're telling you to do this first. And then once we do that first, we can then move on to the next part of the procedure, right? All right, so into the dunk tank, that oil goes. Then number 4 says make a methanol and KOH solution. So the procedure here, making the potassium methoxide. So using a 50 ml graduated cylinder, measure out the correct volume of methanol under the fume hood. Okay, that's not a big deal. I did that calculation up above. I know how much methanol that I should be using. It tells me that I can use a graduated cylinder for this. I don't need to pipette it, so don't act crazy with it. So graduate cylinder, in goes the methanol. Not a big deal. Then it says number 2, using a balance, weigh out the correct mass of KOH. All right, so that math was from up above. So if I've got that math correct, I just measure out that many grams of KOH. KOH is a solid, so this is not KOH liquid solution acting as a base in that regard. This is KOH crystal. That is how those liquid solutions are made. It's just like NaOH. Sodium hydroxide is a crystal that we dissolve in water to make a base or a solution of sodium hydroxide with. So this KOH is the solid form, not the liquid form. I just need to make that clear. And you're going to take that solid KOH and you're going to measure that out on a balance until you get to the appropriate amount. It says do this quickly as the base is hygroscopic. Woo! That's a fancy word, and that just means it gains water and it gains moisture from the environment very quickly. So it loves to be thirsty, and it's going to reach out and grab all of that water from the atmosphere as much as it can, and then if you just leave it sit out onto your countertop, you're actually going to see probably a pool begin to get formed of liquid in the wave boat when there was no liquid in there to begin with. And that's because KOH is all the water out of the atmosphere. Number 3, it says dissolve the KOH in the methanol. So I'm going to take a beaker, and that beaker is going to have my methanol in it, and then it's also going to have my KOH in it as well. That is a liquid solution. KOH dissolves very well in water, but it needs a little help in alcohols, right? And here's where it needs a little bit of help. So it says it will require a little bit of low heat, possibly. So what I like to do is I like to put the beaker onto a very low, warm, hot plate and turn the stir wide open. And then that KOH will dissolve, but it's going to take a little bit of time. So again, don't rush it, because you've got oil over in a water bath that needs to heat up to 55 degrees anyway, and that's going to take a little bit of time as well. So as you are dissolving slowly that KOH crystal in the methanol, then not a big deal. If that's going to take a little bit of time, go do something else. Your oil is heating up and it's coming to temp and it will not overheat. Your KOH is dissolving in the methanol. That doesn't need your attention. And then go do something else. Get another lab prepped. I don't know what you want to do, but do something. Don't just sit there and watch grass grow in the lab environment. Then it says you can also just leave it overnight, and that's okay too. But if you're heating it or you're leaving it for an extended amount of time, you want to place a cap or like a watch glass or something on top of those containers, so that way the methanol doesn't evaporate off. You don't want that total volume to change too much. So you really do want to make sure that that volume is 50 mils or a little bit above, because if not, that might not be enough liquid solution in order to get your biodiesel to be properly made. So we need that volume pretty importantly. All right. Next, it says once it's fully dissolved, add the solution to the canola oil sample or vegetable oil sample, and then carefully and slowly stir the mixture for at least 180 minutes. Oh my God, that's 3 hours. The solution should remain at 50 to 55 degrees. Next up, turn off the heat and the stir. And then number 7, allow the mixture to stand for 48 to 72 hours. Oh God, that is making biodiesel. That's what you need to do. So I told you it's not very difficult. It's just going to take a lot of time. And now you see why. So once they go into the jacuzzi and once it begins to stir, this is a time for you to walk away and you tell me, or someone else that might be helping out in the lab, you tell me, turn off my biodiesel, please. And in 3 hours, because you're going to write down what time you started it, and in 3 hours time, I'll go and I'll turn it off for you. That way you can go work on other stuff, or you can leave for the day and not worry about it and feel like you've got to stay 3 hours just to turn a heat button off. It is not a big deal, I promise. After the 3 hour timestamp, I will go to the water bath and I will turn the water bath off for you, so that way you do not have to be there. That's all that you're missing out on, and I don't think that's very complicated to do. So let me know and I'll go and turn your power off at the time that you tell me to do that. Next up, it says allow it to sit for 48 to 72 hours. So normally what happens here is that I do lift it up out of the water bath in case someone else needs to use the water bath. So I will lift it up out of the water bath for you. It's probably going to be on a clamp. It's not a big deal. And I will clamp your sample on the rack or on a ring stand that is located near the water bath. So your name's going to be on it. It can sit there for another 48 to 72 hours. That's 2 to 3 days, folks, right? 2 to 3 days, it just needs to sit, and it just needs to hang out with you doing nothing to it at all. Don't disturb it. Just let it do what it needs to do. And then after that 2 or 3 day time period, you're going to come back in, and then you're ready to be picking up with the rest of the procedure that you're going to see that follows this. All right. So in the next video, we'll talk about the next part of the procedure, and that's the separation of the biodiesel. What's going to happen during this stage, and what do I need to watch out for? But this is it, folks. This is the reaction, and that's all that you need to do. Add some stuff in a hot water bath, and then just let it hang out, walk away, forget about it, do something else, and then come back to this a little bit later on. That's it. It's not difficult, and I'm even doing some of the work for you. I'm turning off, got the hard job of turning off that power button on that water bath. All right, so I'll see you in the next video, and we'll talk about separation.